Hi, in this lecture we are going to cover reactions of alkyl halides, nucleophilic substitution and elimination reactions. The chapter will include first the discovery of nucleophilic substitution reactions, and then we will start SN2 reactions. Then we will cover characteristics of SN2 reactions. Then we will go to SN1 reactions. Then we will finish the chapter with characteristics of SN1 reactions. We are not going to cover elimination reactions in this chapter. Let's start. As you remember, a substitution reaction is a reaction in which a nucleophile substitutes a leaving group. That's the reason why we call a substitution reaction. In elimination reaction, however, two groups or a collection of elements are eliminated from a structure. Generally, we form alkene products. That's the familiar, or that's the prevalent reaction in organic courses. Okay, why an alkyl halide undergo substitution reaction, and why an alkyl halide undergo an elimination reaction, we are going to explain in this chapter. So let's start. A carbon halogen bond in an alkyl halide is polar because of the electronegativity difference between the halide and the carbon. And halides are more electronegative. For that reason, carbons will be electron poor and halides will be electron rich. And alkyl halides will be electrophiles because of the electron poor carbon nature. And that's the reason why a variety of nucleophiles can attach itself to alkyl halides and substitution reaction can happen. In a nucleophilic substitution reaction, we have always an electron-rich nucleophile, and if you look at here, this is the nucleophile and its electrostatic potential map. As you see, it has a dense red region around itself, and for that reason it's a nucleophile, and we call it as a Lewis base. Then if you look at our halide, let's say alkyl halide, because of the electronegativity difference between carbon and halogen atom, carbon in the electrostatic potential map has a blue region around it, which means that it is electron deficient or electron poor, and it makes it an electrophile or Lewis acid. It can accept an electron pair from the Lewis base, which is also nucleophile. So what happens in a nucleophilic substitution reaction? This is true for SN2 reactions, which I will explain. A nucleophile attacks the electrophile, or we will call in this chapter electrophile bearing species as substrate. So a nucleophile approaches to substrate and replaces the leaving group, and it attaches itself to the electrophilic carbon. So we are going to see the details of this reaction in the coming slides. Let's start defining different types of substitution reactions or nucleophilic substitution reactions. The first reaction we are going to see is SN2 reactions. What is an SN2 reactions? Basically, S refers to substitution, N refers to nucleophilic, 2 refers to second order reaction. If you look at this particular reaction here, a hydroxide nucleophile is reacting with a substrate, which is an alkyl halide, bromomethane or methylene bromide, and what is happening? Nucleophile add itself to electrophilic carbon. Here we are forming an alcohol, and Br we are going to refer it from this time on as leaving group, because it's leaving the substrate. So again, let's define. Hydroxide is nucleophile, bromomethane or methylene bromide is substrate, and we form the substitution product. It's an alcohol, methyl alcohol or methanol, and bromide ion left the electrophile, or we call it as a leaving group. Okay, let's look at the reaction. This reaction is a single step reaction, and the stoichiometric coefficients for reactants are 1 to 1. So this is a 1 to 1 reaction, and this is also a rate determining step. We don't have any other steps. For that reason, this step is also rate limiting or rate determining step. If we analyze the reaction kinetics for this reaction, for this particular reaction, we can write reaction rate is equal to K, which is rate constant. It is a particular constant for every different type of reaction, and then the concentration of reactant, first reactant and second reactant. And if we look at the stoichiometric rate coefficients 1 to 1, so here we can write 1 to 1. So I'm going to write the powers as 1 and 1. If you add up the powers, it's equal to 1 plus 1 is equal to 2. So these types of reactions are called second order reactions because the summation of the powers equals to 2. For that reason, we call this type of reactions as substitution reactions, nucleophilic substitution reactions, and second order. And if you look at here, this is a nucleophilic substitution reactions. Sometimes we call it bimolecular. Bimolecular means that we have two molecules involved. A bimolecular process can be second order or can have more order, but if the coefficients are 1 to 1, stoichiometric coefficients or stoichiometric ratio is 1 to 1 between reactants, we call it a second order, and still it's a bimolecular process, or it involves two molecules. So basically, if you increase the concentration of hydroxide ion 2 times, the reaction rate is expected to increase 2 times. If you increase the concentration of the substrate 2 times, again the rate is expected to increase 2 times. So it is the rate linearly dependent on the concentration of reactants. So that's the reason why we call SN2 reaction: substitution, nucleophilic, and second order, or we can call it second order or bimolecular process. This is what happens in an SN2 reactions. In an SN2 reaction, we are going to analyze basically the mechanism. So the mechanism involves this: a nucleophile, which is generally a negatively charged and electron dense. Here you can see it, hydroxide. So it is approaching to the substrate having leaving group. Then what's going to happen? We are going to form a bond, a sigma bond between oxygen and carbon, electrophilic carbon. Then the leaving group will leave. So carbon bromide bond, bromine bond will break. So this is the curved arrows we can show this way. So these are reactants. What happens in the transition state? In the transition state, the bond between the nucleophile and the substrate or electrophilic carbon partially forms. That's the reason why we draw as dots with dots, and the bond between carbon and the leaving group is breaking. And we can show the transition state as a planar structure, carbon having three sigma bonds and also 2 partial bonds. One is forming, one is breaking. So this is like you can say the molecular shape, molecular geometry is we can call it trigonal bipyramidal. But what's going to happen? Again, we will form an sp3 hybridized product. The electrophilic carbon will be sp3. So what's going to happen in the as the reaction completes itself? The nucleophile carb electrophile bond will be formed completely, and the bond between carbon and the leaving group will be broken completely. So, and if you look at here, electrostatic potential map, nucleophile having a red dense electron region and the electrophilic carbon having a blue region. So we form here the transition state, and these are the product. If you look at here in reactants, there are 3 hydrogens around carbon, and it's facing towards nucleophile. But in the reactant, what is happening in the product? What happened? These hydrogens are facing not the nucleophile or bonded nucleophile. It's facing right side. Here it was on the facing left side, here on the right side. So what happened? The configuration here inverted. You can think of nucleophile as a wind, and you can think of this carbon with 3 groups like an umbrella, interior region of umbrella. What happens in a rainy and windy day? If your umbrella, interior part of umbrella faces the incoming wind, so it will be inverted, right? So what happens if you start with a chiral substrate? The product is going to be the opposite configuration. We started with S2-bromobutane for this particular reaction. When bromine replaced with hydroxide, as you see here, the configuration inverted. So we obtained an R product. I'm going to show you an animation showing or a modeling calculation basically showing this process. Okay, here we have the same reaction basically. What we have here chloromethane, and we have here hydroxide. This is nucleophile, this is substrate. What happens if they react with each other? As the time passes, hydroxide is going to approach to the substrate, and I would like to show something here. So this is almost a transition state. What happened in the transition state? The bond between carbon and oxygen partially formed, and the bond between carbon and, this is chlorine. I'm going to show you the symbols also. The bond between carbon and chlorine is almost breaking, and this is transition state. And as you see, this carbon is almost planar. If we go back one more. So one more requirement for SN2 reactions: the nucleophile has to approach to the electrophilic carbon 180 degree away from the leaving group. So basically hydroxide cannot approach from this side or from this side, but it has to approach from the opposite side. So if we make bond between a leaving group carbon and nucleophile carbon, the angle has to be 180 degree. So that's a requirement, and as time passes, you see the configuration inverted. Let's go back to the original. As you see, hydrogens are facing towards nucleophile, but after the reaction, hydrogens are facing towards the leaving group. So the configuration of carbon is inverted. If this is a chiral carbon, so the reactant will be and reactant and products, they will be with different or opposite configurations. Okay, let's move on. Let's solve a question related to SN2 reactions. Assign configuration to the following substance and draw the structure of the product that would result on nucleophilic substitution reaction with HS minus nucleophile. Let's say reddish brown is bromine. So this type of questions I always prefer to draw skeletal structure, and since here we have a chiral carbon having the leaving group, this is bromine, so I would like to draw 3D representation of the chiral center with skeletal drawing. So 1, 2, 3, 4, 5. This is a pentane, and the second carbon and the fourth carbon has substitution. So let's draw this way. Let's draw a little bit better. One, two, 3, 4, 5. So here we have 5. So there is here a methyl. This carbon, so I'm not drawing 3D representation because this carbon is not chiral. Why? Because it has two methyl groups. But this carbon is a chiral carbon. So I would like to draw H as dash representation, meaning that it's going away from the plane, and it's coming out of the plane, the bromine. So I'm going to draw this one as a wedge. So this is bromine. So what is the reaction? The reaction is between SH minus and this alkyl halide. This is negatively charged. So let's firstly assign the configuration of this chiral carbon. Is it R or S? So as you remember, we use Kahn-Ingold-Prelog sequence rule. Hydrogen is number 4. Bromine has to be number 1 based on the atomic numbers. This methyl, and there is here an alkyl fragment. So this is going to be number 2, and methyl has to be number 3. And hydrogen is facing away from the plane, screen plane or paper plane, as if you want to call it. So let's look at 1, 2, 3. From 1 to 2 and 2 to 3, the rotation is counterclockwise. So this chiral carbon should have S configuration. So what's going to happen after the reaction? The reaction has to produce the opposite configuration. So I'm going to draw it again. So a methyl. Again, I'm going to use the same drawing style. Let's not write H here because H will not be there anymore. Okay, so what's going to happen? It will be inverted. So hydrogen, instead of going inside the plane, so it has to come out of the plane, and Br, but since what's going to happen, this reaction is going to produce a substitution product, right? So what's going to happen? Sulfur is going to attack here, and Br will leave. So we have to show this product. So here we should have SH plus Br minus. So what's going to be the configuration of this product? It's going to be, since we started with an S, it has to be R configuration. You can test it. Okay, let's move to the characteristics of SN2 reactions. Well, characteristics of SN2 reactions are related to rate of SN2 reaction, how fast or how slow a reaction. As you remember, the rate of a chemical reaction depends on activation energy. We have here two different reactions, let's say, and the first one is the red one, the second one is the black one. If you compare the activation energies, the first one having red curve, it has lower activation energy than the reaction represented by black curve. So red one is faster than the black one. This reaction is faster than this one. Why? Because it has lower activation energy. So how can we change rate of reaction if we change some parameters? Basically, let's say that if we change reaction conditions, and if the transition states between different reaction conditions is the same. Let's say the transition energy is not changing, but if we change the reactant energies, the activation energy is going to be different. So let's say that we change reaction conditions and the reactants have higher energy. So what's going to happen, since they will have the same activation, the same transition state energy, the reaction will be faster. So, or let's ask this question: how can we make a reaction faster? In two ways. The first way, we can keep the transition state energy same, but if we stabilize, like from red to black, black reactants or reactants at the black curve is more stable because having less energy. So what's going to happen? They will have more activation energy, so black will be slower. Or if you start from the black, if you destabilize the reactants, or if you increase the energy of reactants, what's going to happen? Reaction will be faster. Or a second way, if we keep the energies of reactants same, but if we stabilize or destabilize, or if we increase or decrease the energy of transition state, the reaction rate will change. For example, here the black one is faster. Why? Because it has lower activation energy. Why? Because the transition state for the black reaction is lower. So the activation is lower, so reaction is faster. So basically, if you can change the activation energy, you can change the reaction rate. But how about this effect for SN2 reaction? The first effect, let's see, steric effects in an SN2 reaction. Let's compare 5 reactions. We have an alkyl halide and we have a nucleophile. What's happening? Nucleophile is replacing the leaving group, and we have an SN2 reactions. If we keep everything, all the experimental conditions same, but if we change the structure of substrate, alkyl halide, what's going to happen? Let's see, if we have a methyl halide, methyl bromide, if we have a primary halide, primary bromide, if we have a secondary bromide, if we have a neopentyl bromide, this is a primary, but this carbon has 3 methyl groups, so its name is neopentyl. We have 5 carbon and its name is neopentyl bromide. And if we have a tertiary halide, you remember what's primary, secondary and tertiary? The functional group bearing carbon has no carbon, so it's called methyl. If the functional group bearing carbon has one neighboring carbon, this is called primary halide. If the functional group is halide, this is a secondary because the carbon bearing the halide is a secondary carbon, secondary halide, neopentyl and tertiary halide. The reaction rates found to be this way: methyl and primary halides are much more faster than tertiary neopentyl, or we can say that the methyl halide, methyl bromide, is the fastest. It's 2 million times faster than neopentyl, or even more than tertiary halide. So what's the cause? We have the same nucleophile, we have the same experimental conditions, only the structure is changing. The bromide bearing carbon has different neighbor. Let's look at here. If we have methyl bromide, so what's going to happen? A nucleophile has to approach from back and has to replace the leaving group, right? So since we have 3 small hydrogens around the electrophilic carbon, sterically it's very feasible or open for nucleophile to be able to approach. But if you change one hydrogen to a methyl, or 2 hydrogen to 2 methyl, or even this is tertiary, so we are blocking the electrophile, and the nucleophile will not be able to approach because these bulky groups, big groups, are going to repel or shield the carbon. So OH, our nucleophile, if it is a hydroxide, will not be able to approach easily, so that will translate into higher activation energy. But in terms of the previous slide, so this is the case. So what's happening here? We have we have lower activation energy. Why? Because this is, let's say, for primary halide. So this is the leaving group, this is the nucleophile. Nucleophile can easily approach this carbon and can replace the leaving group. So this is the structure of transition state, and transition state will have less energy compared to what? Let's say these are all hydrogens for the methyl halide, but if you have a tertiary halide, let's draw a tertiary halide SN2 reaction as a transition state. So nucleophile will not be able to easily approach to this electrophilic carbon. So this one, because these methyl groups will repel or it shields the carbon, so what's going to happen? Nucleophile will not be able to easily approach here, so that will translate into an increase in activation energies. The reactant energies are more or less same. It's not changing too much, but the transition state is going to have more energy or will be less stable when we have a bulky substrate. So that's the effect. And another thing, I'm going to show you some models representing methyl bromide or methyl halide versus T-butyl tertiary bromide. So I'm going to show you methyl halide, and we are going to see this one. If you look at here, this is chlorine. Let's show you the symbols, and if there is a nucleophile, the nucleophile will be able to easily approach this carbon. And generally in organic chemistry we show a space filling model rather than ball and stick model, and that will depict why this is sterically open, this carbon. Okay, as you see, this is a much more accurate way of showing molecules with true van der Waals radii, or like true sizes of atoms. So as you see, this carbon, this is the black or gray, let's say gray, so it's basically open because hydrogens are very small in terms of size. But if you have a tertiary halide, I'm going to show with the same way. So this is a tertiary T-butyl chloride. Okay, so a nucleophile has to approach this carbon from the back side. So let's see how the space filling model will show us that this reaction will be, or the nucleophilic substitution reaction will be smaller. Okay, as you see here, this is the electrophilic carbon. It's almost blocked by 3-methyl CH3 group. So if you are a nucleophile, you will not be able to easily approach this carbon that we cannot see almost here. So that's the reason why T-butyl chloride reacts almost 2 million times, or 2-butyl bromide, that was the example, 2 million times slower with respect to methyl bromide. And one more thing, vinyl halides, which is a halide in which the halogen atom is attached to an sp2 carbon, or aryl halide, in which the halogen attached to the ring directly, benzene ring. Nucleophilic substitution reactions, SN1 or SN2 reactions, cannot happen because the back attack is not feasible because of the steric factor. So don't forget, this is a general rule. Okay, what is the next factor that affects the rate of SN2 reactions? This is we are going to discuss this effect in the next lecture. Thank you so much for watching this lecture.